Hello everyone, welcome to season 2 of the Periodic Roundtable. And of course, I'm Joel.
And I'm Brittany.
And we have a very special guest today. Peter, would you like to introduce yourself?
Sure, my name is Peter, or actually if you see my name, it's spelled with a second E and it's pronounced Petr, which for some reason gives people a lot of trouble around here, so Peter is fine. I'm a plasma physicist, even though I work at the engineering department. I'm from Central Europe, came here to get my PhD. So now I'm a postdoc at Virginia Tech.
You ended up in Virginia Tech doing plasma physics in the engineering department.
Yes.
How did you get all the way over here from Europe? What got you started in plasma physics?
In plasma physics? Right, so when I was, first of all, I probably should start at colleges work slightly differently in Europe in general, and we get specialized from day one. So nothing like doing engineering and, I don't know, Middle Eastern literature together, right? Taking classes for credit you need. So I went to college which was just physics from the day one. So my bachelor's degree was general physics, and then for master's degree, or to be precise, the last year of bachelor's, I got specialized. And they told us to, after we do the first semester of exams, because that's kind of, again, it works slightly differently. It's kind of a proof that you have what it takes. Because especially for my university, it has a reputation of being pretty difficult. And there were also no entry exams. So they were taking everyone. There was like so few people applying for this school because it has this, well, it's one of the schools in my home country when you mention a name, people are like, oh my god.
That one.
Okay. Yeah, so getting there means nothing. Staying there after the first set of exams, that means something. So they were telling us, okay, after the first set of exams, you should start looking at the different groups and, I don't know, ask them to, if they have some job to do or something like that. And this is a funny thing because, as I'll mention in a moment, I ended up getting the full circle. I wanted to do simulations.
Okay.
So I wanted to do like numerical models and work with computers. And I went to the department that did the numerical simulations, and they were super excited that I'm interested, but they did not know what to do with me. Like, they had no clue what kind of appropriate job to give me. So they're like, okay, it's amazing, we'll give you these few papers to read and then we'll figure out something. And they gave me the papers and I did not understand a word. So it was very, very disappointing. And I think I never showed up again at the department.
Oh, wow.
Because they really didn't know what to do. And then one of my professors was like, okay, so let me show you a bunch of people here for something like a recitation. Show our department. It was a big department. It was Department of Surface and Plasma Physics, which is like a weird combination. It was for historical reasons and like stay there because, you know, they were together, they had a big budget, so that when some group needed more budget than the other group, they were kind of flexible with that. So it was mutual, beneficial symbiosis, even though it really had nothing to do.
Huh.
And he really wanted me to get to work with him on the surface physics part, the thing that he was interested in and like his part was. And then he was like, okay, then just, you know, to give you the full picture, let me take you the one upper floor where there was the space physics, the people studying the space weather. And I entered there, and I remember my first impression getting all the doors being covered by like marks from space, you know, different space missions. They have these logos. And all those doors were covered with logos of the space. Like, I'm like, okay, that's interesting. And then I talked to two really nice old professors that were like leading this part. And they were like, so we have this new instrument that we built here, and it was just launched on a spacecraft. And we are getting data, and if you are like interested in doing the spacecraft analysis of a spacecraft data of solar wind, we'll be like happy to take you. And I was like, okay. And that's how I got into plasma physics.
Wow, that's so awesome. So, seeing all the space stickers, that's exciting.
Yeah.
I would get excited if I saw any door with space stickers. Immediately want to walk through that door.
Oh yeah, absolutely. So I had a question, more for our listeners than anything. So most people, when they think of plasma, they think of the stuff in your blood. So can you explain what exactly plasma is as a state of matter?
I see, we're starting with tricky questions. So I'll get to the name in a moment, but kind of one good way how to think about plasma is as a fourth state of the matter, which is not 100% exact, and I'll get to why. But so if you look at the three standard states of matter that everyone knows, right? Solid, liquid, and gas states of matter. If you start with solid and you add heat, what happens is you get a liquid. If you add more heat, it evaporates, you get a gases. And then if you add even more heat, more energy, then what happens is that from the electrons from the molecules and atoms start to tear out of the atoms and start forming this very weird state of matter where you have ions, which usually are positive. There are some exceptions there. And then you have electrons, so it's kind of like a soup of these two things together. So it's kind of like gas, but also reacting to electromagnetic forces. The reason why I said it's not 100% exact that it's fourth state of matter is because between the other three there are strict boundaries, right? You have either solid or you have a liquid.
So like phase separation.
Yeah. There's a phase separation, but with plasma, there is no clear phase separation because you can have different states of ionization. The process of creating plasma is called ionization, where you tear the electrons from the atoms, and you can have different percentages of ionization. So, for example, the solar wind, the plasma I mentioned that I studied in my master's and undergrad, that's pretty much 100% ionized. So it consists of it's mostly helium and hydrogen. So ionized hydrogen is just protons, right? So solar wind are mostly protons, electrons, and then some helium cores, which are called alpha particles. Two protons, two neutrons, right? But you can also have a very weakly ionized plasma, which is, 5% is ionized, the rest is neutral gas. So that's why it's not a clear distinction. And the name is actually interesting because the name is coming from the blood plasma.
Really?
This whole field of plasma physics started in 20s, not 1920s.
We're now on these.
Yeah. And one of the first scientists were from Russia. So one of the name that every plasma physicist known is Langmuir, and he did in 1921 or 23 are the first papers. And when he was studying the plasma, this concept of heavy ions floating in this soup of electrons really did remind him the blood particles flowing in the plasma, right? It's like the plasma, and then you have the, I don't recall how the blood particles are called, but it really reminded him what he was seeing in the plasma I studied. So when he was studying the plasma as a state of matter, it did remind him that the plasma as a blood plasma.
Okay, so as a state of matter for plasma, since most people think about it as the blood, or another common idea is like the sun, what is plasma in terms of what people can see on a day-to-day? Because plasma is the most abundant state of matter in the universe, right?
Yep, that's true.
So it's all around us. Where can people see it?
I wouldn't necessarily say all around us. It's the most abundant state of matter because if you look at space, it's pretty empty and it's mostly stars and not us, right? Even in terms of our solar system, if you, that's the funny thing I always mention, if aliens come to the solar system and they ask what is the solar system? And you say, yeah, our solar system, that's sun and nothing else. Then you are actually pretty accurate, right? In terms of just volumes and masses, sun is really, really huge. And then if you're okay, maybe I want you to be a little more accurate, so then you add Jupiter. And then because Jupiter is still 2.5 times heavier than everything else. So everything around us is a really small part of the universe. So in that perspective, yes, plasma is the most abundant state because we have stars and we have winds from the stars, and that's what the universe actually consists of. Well, talking about the standard matter, not going to dark matter and dark energy and stuff like that, which probably would be for different podcasts. But so on Earth, the plasma is not that abundant, but we still can see it. I'm a little hesitant to mention this because fire is often used as an example of plasma. But not every fire, it's not as simple to say every fire is plasma. Fire can, because there are some additional conditions that technically need to be satisfied for we call it plasma. So some additional parameters. But yeah, fire can be plasma. Another good example are lightnings and discharges and stuff like that. So if you ever use discharge to weld and stuff like that, and discharge, you have ionized gas, and that's plasma.
Very cool. So my question is, why actually study this? Why study plasma physics?
So, my first answer to that would be because studying even very basic physics is good, and you never know what can come out of it, right? If you just do the general physics, not just physics, even math, even like really abstract things like studying group theory, then you do this whole abstract math, and then you realize, wait, if you look at crystals, this math theory we developed completely independently and was super abstract suddenly describes this in the real world. So I'm a big fan of doing just basic physics, just for the purpose of understanding the universe around us. But I know that this doesn't hold with all the people, and I'm lucky that plasma research actually has a really important applications for I would even say day-to-day lives. I started talking about the solar wind, right? And solar wind is something that can have a huge ramifications for life on Earth, because this stream of charged particles and currents can induce currents in our power grids and cause damage to our networks and stuff like that. So there have been cases of blackouts caused by the extreme solar weather.
I've heard of scenarios, like doomsday scenarios, where a huge solar flare would wipe out all of our power grid. So
Yep.
something like that.
Yep. There was one in 2004. These things are called coronal mass ejections, when literally huge bunch of coronal mass from the sun gets ejected from the sun and then flew through the air. Luckily, that one went the other way. But if it hit the Earth, it would be like Middle Ages here, and like with candles and no podcasts and
Wow.
horror. So yeah, understanding this and how it works. For one, enables you to predict these things, and then also maybe strengthening the infrastructure and stuff like that. And that's solar application. Then we can get more down to earth, and we can get to electricity production. So you might have heard about fusion as one of the concepts for possible production of kind of unlimited source of clean electricity.
Right, cold fusion, the whole thing.
Oh, cold fusion is that's very, very interesting story. That is kind of about not to do in terms of it shows a very unhealthy approach to science and publications, and doing the press conferences before you get a peer-reviewed article and stuff like that. So cold fusion is an example of very bad science. but the hot fusion is so hot fusion is the process that happens on sun. Right? So there is a lot of energy in the particles or in atoms, and you can release this energy either by fission, when you take the heavy ones and you make do the fission and you make a small ones out of them, which is what people know how to do. And we have the nuclear power plants, right? You have those rods and you do the fission, and then you heat the water, create vapor, create electricity. Also, you can create bombs as well. And if you take the lighter ones, it works the other way. If you take two hydrogen atoms and you fuse them together, you release the energy. The issue of that is that atoms, and especially the cores of atoms, as they have all the positive signs, they don't want to go next to each other, really. So in order to get them close enough to start fusing, you need to have really hot, dense, high pressure conditions. And people know how to do it explosively, so that's what the hydrogen bomb is. And then we know how to do hydrogen bombs for many decades at this point. The issue is how to do this in a lab. So how to do this and not blow yourself up. So that's one of the applications, because that's all plasma at this point. So.
Wow, that's fascinating. So you have plasma physics, from the basic understanding of fundamental physics, can lead to future devices that sometimes aren't necessarily understood yet. But then getting closer to the everyday, you can see things such as solar wind and start studying some natural phenomena that we can observe. Then getting even closer to everyday, with this fundamental understanding, you can get closer to energy production, which would definitely help. For example, like coal-fired power plants is one of the largest productions of CO2 and green gas emissions. So looking at other things such as plasma might be beneficial for not only us, but decades and millennia in the future.
Yeah, because then you have no nuclear waste, and your fuel comes from the seawater.
Right, which is absolutely fascinating. And just for reference, you said you have to have really hot conditions and high pressure conditions, right? So right now, it's like, I don't know, 30, 40 degrees outside, Fahrenheit.
Yes. It's very cold. It's very cold in Newfield, of course.
So somewhere around 0 degrees Celsius, and we're just above sea level, so a little bit less than 1 atmosphere of pressure. So for our listeners, can you give us like a reference for what you would need in extreme conditions for a laboratory setting?
So these things, we are reaching the levels when the classical understanding of temperature and pressure is no longer really makes sense. We are talking about millions of degrees. But this thing is not that you heat your lab, right, to a million degrees. Usually it's like some vacuum chamber, and in the middle you hold this really hot plasma. And one thing that actually is still an open question, it's more like an engineering question, is how can you make this super hot plasma not to touch the walls of your chamber? And that's usually where magnetic fields and stuff like that comes in. But in these states, our understanding of what temperature is really no longer holding. So, for example, even the solar wind, the temperatures are really, really hot, but it doesn't mean that if you stick your arm into solar wind that you get burned. Because, yes, the particles move really, really fast, which what the temperature is the chaotic speed of the chaotic movement of the particles. But there are so few of them that it would not hit you at all.
Huh. Weird.
In the solar wind, that's that's another very interesting thing about plasma physics, because the scales we work on are really different. So, for example, I keep going in solar wind because it's one fascinating topic. Even though I don't really work with solar wind right now, we are talking about particles per centimeter cubed, right? Like tens of particles.
So few.
Yeah, that's way better than the best vacuum people can achieve, right? There are people trying to. Their whole purpose of research is to get a best vacuum, and then you got like those really, really advanced things. Like, for example, one of the concepts is you're literally freezing the particles, right? You put a cold piece into your chamber, and then you are cooling it, and then literally the particles that are moving, the so few particles left in the system, then they freeze on this thing. And still, the particles you end up with are the volume is much denser than what you have in solar wind. And even though the solar wind can have very serious consequences on Earth, as I mentioned. So that's a really interesting thing about plasma physics, that the scales that this applies goes from really hot and really dense to literally nothing.
Wow, that's so cool. So I wanted to get a little bit further into your field of expertise, right? So it's really hard to reproduce plasma in a laboratory setting to study it. So if my understanding is correct, you do more like modeling and simulations,
Yes.
right? So if it's really hard to produce this in a lab, then in order to make just a little bit of plasma, it'd be super expensive, right?
That really depends on what you're trying to do. You can get some plasma pretty cheaply.
Okay.
Ionize, well, you just need some electrodes and you can ionize your gas in the chamber. The issue with doing the experiments is that plasma is really hard to measure. And that's because, as I mentioned in the beginning, the plasma consists of charged particles, really light electrons, moving kind of freely in plasma. And there's this one fundamental thing of plasma called collective behavior. Plasma reacts to electric fields. So if let's say you want to measure electric fields, so you would think, okay, I stick a probe and measure a field. The issue is that plasma will rearrange itself around the electrode, shielding the electrode out, making your measurements kind of different than when the probe wouldn't be there. So optical measurements are a thing. And yeah, if you want to do those like big experiments like for fusion, that's expensive.
So the alternative instead is to do simulations, which is what you primarily work on?
I wouldn't say alternative really. I don't want to come around simulation people and theory people and experimental people, people who do experiments kind of give each other a hard time continuously, right? Making fun of each other.
Same in our field.
Yeah, I imagine. But really, you need both. So I don't want to sound as a guy doing simulations that never touched a real thing in his life, which is actually true. But really, it's kind of one of the emerging fields recently in simulations, something called verification and validation, which is a rigorous field of how to make sure that you're not simulating a complete nonsense. And it is really important that simulations and experiment work hand in hand with each other, right? Simulations can give you insight into what's happening in the experiments. You have a better field of view, to put it that way, that when you do the simulation, you know about everything that's happening in the system, right? You're not limited to where you put your probes, and you can focus on some parts, and you may tweak the parameters easily in your simulation, and it may be really helpful to you. But then, if you never verify that your code actually simulates something that we can measure, then you might be just drawing the images by hand, and it has pretty much the same value, right? If you just write a code and you go into simulating something and you never did any verification, then it's kind of worthless, really. So yeah, I do the simulations, but we're at this point we are trying to develop the code, and there are definitely some experiments that we want to run with our colleagues and do some verifications as well.
Okay, so you need that validation and verification for your code, so that you're actually studying something rather than making it so esoteric you don't know if it'll work on real-life plasma.
Well, the thing is, yeah, pretty much. So one of the professors at Virginia Tech, he's actually one of the leading experts in verification and validation. He's a Professor Chris Roy, and he teaches a class about verification and validation, and he was mentioning one case they did, and mostly this thing is being developed for aerospace applications, so flows around airfoils and stuff like that. And he mentioned this one story when they were doing some simulations of a flow, and they were doing the validation with wind tunnel data, and they got the results from the experiment, they got the results from the simulation, and they were totally different. Something like completely misaligned results. So they went back to the code and they found some bugs. There were like some things in the code that should not have been there, some errors introduced. So they fixed them, they fixed the bugs, rerun the results, and they were still getting, it was better, it was closer, but they were still getting different results. And experimentalists, as they do it, like, oh no, we are fine, it's still in your code, right? But then they actually convinced that there's nothing left in the code that could be wrong, and they forced the experimentalists to look at the data, and then they realized they're actually measuring the results at slightly different position, if I remember correctly, than they were supposed to. So this was this example of mutually beneficial thing when it helps increase the fidelity of both the code and the experiment as well. So this is what I'm talking about. What I do is we have a couple of fundamental equations in plasma physics, and we write a numerical code to solve those equations. But because these things are never as easy as it gets, you usually make some approximations, and also you need to code it correctly. So you need to make sure that you're using the right equations and transferring them into your code per se in a correct way.
Wow. So you have to take the fundamental principle model equations, which usually take approximations. So for example, like first principle quantum mechanics models?
The plasma physics, there are some.
Okay.
There are some plasma physics models that you go into quantum. Usually no, not. So we don't really introduce quantum mechanics into plasma physics code.
Okay. So the approximations, is that because you can't get a actual value? For example, electrons above a one electron system, you can never know the exact position and the exact momentum. So do you make those approximations, or is it more of a cost-benefit analysis for how long your computer takes to run these programs?
Yes. So again, the quantum effects are really not taken into account in most of the plasma physics code, at least as far as I'm aware. So our electrons are solid ball. So if you're running into this, there are a couple of ways how you can simulate a plasma. First, I think kind of the simplest one to imagine is just particle-based model, where you have particles. You can treat them as little balls. Really, no quantum physics here involved. And then the simplest thing you can do is you say, okay, so my particles are reacting with each other electrostatically, right? Do the Coulomb law, you multiply the charges, divide over the distance squared, and you have force between those two particles. So then, what do, you take these equations of motions with the forces, and you need to, so the key word here is the discretization, because all the things in nature and in time are continuous in time. But we really cannot do this with computers. We are limited to discrete numbers. So discretization is the keyword here. So what you do in this particle code, you look at your system in like one snapshot in time, right? At one point, you know where all the particles are and how fast they move. Then, because you know where they are, you can calculate the forces on the particles. From the forces, you get acceleration in the particles, which modifies your speed, right? So then you kind of do next time step. You move your system forward by some set amount of time, and with the forces you modify the velocities, and with the velocities you move the particles. So then you move all the particles, and then you have another snapshot in time. And then you do this again and again and again and again until you get to your desired state. So this is pretty much how you solve. It's all differential equations, and if we can solve the differential equation, we are golden. If you can't, we need to do something like that. And even in the analytical theory of the differential equations, you need to have some initial conditions, right? And then you can, or boundary conditions to be precise, and then you can solve some subset level of differential equations. But here we are usually dealing with equations that we cannot really solve analytically. So that we need to do this discretization, but still we need to have something to start with, and then we usually do the discretization in time.
So I actually had a question, moving more away from fundamental aspects of what you study to applications based. So reading a little bit about your work, I saw that you had worked on studying secondary electron emission for Hall thrusters.
Yes.
So I thought this was super, super cool. Can you talk a little bit more about that and explain what a Hall thruster is for our listeners?
Sure. Hall thruster is one of many concepts of electric propulsion. Because we have, at this point, we have rockets, right? Rockets fuel, and where what you do is you burn the fuel, you get a heat out of it, and then you use a nozzle to pretty much convert this heat into kinetic energy, right? And you have momentum coming from your rockets, and based on the Newton's law, it pushes your rocket the other way. That's how rockets work. The general issue of rockets is that you need to carry the fuel with you. So further you want to go, the more fuel you need to carry with you, and the more fuel you are carrying, the harder it is to push your rocket.
Because you're burning fuel to carry fuel.
Yep, you're burning more. This is diminishing returns, right? I don't remember the math now, but when you do some calculations to get to nearest star in some reasonable time, I think you end up with something that you need the amount of fuel corresponding to mass of the Earth or something like that. And it's really, really difficult to get any better because, yeah, you might come up with slightly better fuels. And don't get me wrong, this is very interesting, exciting field. The rocket fuel chemistry is really cool. So if you haven't explored it, I suggest for exploring it in some podcast because it's really, really interesting. But you can get only so much better. And even if you improve this twice, that's not good enough. So classical rocket fuel, where you really burn something and get a heat, classical rocket fuel can get you to Mars. Using it to get farther beyond Mars is really inefficient. And there's where the electric propulsion comes in. The concept is that if you have charged particles, then you can create a thrust by accelerating the charged particles using electric fields. And then your only limitation really is how big electric field can you get. So you need, yes, it's like there's no free lunch. You need to have usually a huge power source, right? And then how you get that. So yeah, it's not like ideal scenario and all our problems are solved, hooray. But generally you can get something way more efficient, and you can get way more efficiency from the amount of fuel you're carrying, because you can accelerate those particles to really high velocities, right? Because again, with the chemical fuel, you get set amount of energy by burning them, right? So you can get set amount of thrust. With electric field, you can just increase, theoretically, you can just like increase the electric field, you increase the energy given to the particles, right? If you have a little higher power source. So electric field, electric propulsion is really nice. I should say this is these are the concepts that are they have a really high efficiency, but they actually cannot be used to lift rockets from Earth, right? So you still need classical rockets to really put all the stuff up to the orbit. But then, if you want to go from there and you want to do some deep space exploration, you really want some efficient engine that can run for a long time.
So you're using the classical like chemical fuel to push yourself away from Earth because of gravity,
Yep.
and then once you are in space, you can use the Hall thrust.
Yeah. There are a couple of different concepts. Hall thruster is one of them. So as I mentioned, the issue with plasma is that it kind of reacts to electric fields. It tries to shield out the electric fields. So you have this problem of, okay, I want to apply electric field to my plasma to accelerate the particles out, but the plasma really doesn't want to have the electric field there, right? So you need to have some usually really clever idea how to overcome this. And Hall thrusters are one of the concepts. They were developed in Russia or Soviet Union originally, and they use this. It looks kind of like a circular slot with really interesting magnetic field setup, and they do it to trap the electrons, because that's one of the fundamental plasma physics things, or not plasma physics, charged particle things. Charged particles don't want to go across magnetic field lines. If you look at the Lorentz force equation, the force acting on particles has the velocity movement of the particle, and then there's the cross product with the magnetic field. So magnetic field is bending the path or trajectory of the particles around the magnetic field lines, which is one of the ways how you can trap plasma, that you put in the magnetic field, and then particles don't want to go across the magnetic field lines. They go along the field lines very well, but not across. But so what happens in Hall thrusters is you have this magnetic field, and you trap your electrons in this magnetic field. And because the electrons cannot move across the magnetic field lines, they cannot shield out the electric field. So then you use the electric field to accelerate your ions. And also, if you have a bunch of trapped electrons there, they ionize the gas for you. Usually, you don't carry plasma with you. You carry neutral gases. For Hall thrusters, it's usually xenon. There are some experimentations with krypton and argon, which are much cheaper than xenon. But that's pretty much it. That you trap your electrons and use the field to accelerate the ions, and then the ions are the thing that produce thrust. The issue of this is that you still have some particles hitting the walls of your machine, and then high-speed energized particles hitting the wall will erode the wall. And that's at this point the biggest limitation of Hall thrusters, that you can run them for 50,000 hours roughly. And then your walls erode to the point where your magnetic coils start to erode, and without magnetic coils the thing stops working. So that's the limitation. It's not how much fuel or power you can carry. It's actually that your Hall thrusters will not live long enough, and if you're in deep space, you can just simply replace the whole thruster. So what I was studying was, again, this was mostly basic physics, but with these applications, we had a really precise and high fidelity model of kinetic plasma physics. And we were studying these fundamental things that are happening when plasma touches the solid surface. And then we were trying, that was a big part of my PhD, was to try to set the specific boundary conditions to study secondary electron emission back from the wall. How does it change this whole scenario?
Wow, that sounds like absolutely fascinating research and technology. So how far away do you think this ideal Hall system with a wall that can withstand that and have a higher lifespan, how far away are we from that?
I think they're getting pretty close. The idea is not having a wall that can withstand it, but I think that's like one of the most promising pathways forward is to change the geometry and magnetic fields so your electrons are actually not hitting the wall.
So if you could perfect a system that kept them from hitting the wall, would that have almost like an infinite lifetime until the electric coils gave out?
Yes, if you can stop your electrons hitting the wall, then pretty much yes. Right, it's still technology, and you still need to have fuel, right? And you still need to have a power source. But yes, that would, if you stop particles somehow hitting the wall and eroding the wall, that would significantly boost the things you can do with them.
Very cool. So you also work on a few other things. And one thing that I was also reading about was you studied, and I don't know if I'm pronouncing this correctly, but tokamak?
Right.
Can you explain what that is exactly?
Oh, yeah.
These were really cool too.
Yeah, that's one thing we already touched on, and that's the electricity production, right? And I said, okay, we have this super hot and dense thing that ideally will start fusing the fuel, producing the energy. And we have a similar issue as in Hall thrusters here. So that's kind of, you might think, two completely unrelated things, but there are many parallels between them. So you don't want this super hot plasma to be touching your wall for two reasons. You don't want to destroy the wall, and for the other reason is it will actually cool down the plasma. And you don't want that because you want it to be hot. And so what do you do? Okay, you say, okay, maybe I can put my plasma into a magnetic field. All right, but the plasma cannot go across the magnetic field lines, can follow the field lines. So what do? You have this, you can create this like tube that you can have plasma in, but then still there are like two ends of this tube, right, that the plasma can go, because that's how magnetic field look like. So what you can do is you can take this tube and you can close it on itself. You kind of create like a donut shape. So if you can create a donut magnetic field shape, which you can by series of coils, then theoretically you can have the plasma just enclosed there, right? Never leaving. Of course, in like real life, plasma can get across the field lines because the particles can collide with each other and they can knock ourselves to like different orbits, and you can have some disruptions like that. So tokamak is one of the concepts for the electricity production. There are, I should say, there are like two general pathways forward how to do the fusion. One is you can confine the plasma magnetically, or maybe three. So one is you just confine the plasma magnetically, you heat it up, and you keep it from touching your walls magnetically in this like typically donut shape like geometry. The other path forward is something called inertial fusion. Then you have this pellet of fuel, and then you implode it. And this is actually really amazing feats of engineering, because there are a couple ways how you can do it. One is called direct drive. Then you have this pellet inside this chamber, and you have huge amount of super power lasers shooting this little, and we are talking, I think it's like a couple millimeters pellet of the fuel. So you have this huge chamber, and then you shoot all those lasers onto the thing, you ablate it kind of again, we are back to rockets. It kind of works like a rocket. You ablate the outer layer of the shell, and then this reaction force will just compress whatever is inside. Again, it creates the conditions you need. Ideally reaching an ignition. And then there are like additional couple concepts. Like one concept that there is actually some research going on in Virginia Tech connected with this is that you take plasma guns and you shoot all the plasma guns again from a sphere to one target, right? You have pellet fuel and you form this thing around it from shooting all the plasma colliding inside. So these are pretty sci-fi concepts. All these things are pulse. So the magnetic confinement can theoretically work on like longer scales, not just one pulse. So tokamak is one way how you can do this magnetic field confinement. Again, it started in Soviet Union and then spread across the world. Currently, it's mostly done in Europe. So there's this one big project called ITER that is currently the largest tokamak being built on the world. It's built in France. It's built in France. They keep postponing the opening, but it's one of these concepts. There are like a lot of questions about whether it will work. At this point, it's mostly about engineering rather than physics.
Yeah.
In my personal opinion, one of the coolest concepts connected to this are something called stellarators, which has a similar concept like a tokamak, but in tokamak you have the field that is like a donut, and then you add a little twist on it. That's for some. This is for stability reasons to get a to stop your particles escaping. When you have a stellarator, it looks kind of similar, but the magnetic field is way more complicated than that. It's really fascinating to look at the images. It's kind of unbelievable shape that is becoming possible to even engineer only recently with the technology and like simulations. And you have those coils that are not circles. Those coils are kind of like circles after a car crash. That is like all around this very weird shape. And to me, a really cool and appealing thing about this is that in the stellarators, you're not trying to really force your plasma into what you want to do. You're trying to create, instead, you're trying to create a shape that is in minimal energy state, really. The most stable state you can get, to put it slightly simplified. So you're really following the laws rather than bending them, which is a weird thing to say because it's really bended. So one thing to look at is W7X. W is for Wendelstein. It's one of the stellarators that's currently being, I think right now they are not doing any experiments. They are in one of the stages of moving the project forward, and they are producing some really interesting results. And it's definitely worth checking just to see how this amazing feat of engineering looks like.
So those are two very different applications from plasma physics that you study.
Mhm.
You have your spacecraft thrusters, then you have something for fusion power. So it really goes to show that like fundamentals are important.
Yes, right. But still, really, even both in the tokamaks and the plasma thrusters, the part we were interested was the layer near the wall. So yes, the regimes of plasma, the temperatures of plasma were completely different, but the underlying physics was similar-ish.
From this talk, and it's been absolutely fascinating. Thank you so much. I've been in awe today. So the fourth state of matter that we have, plasma, this like soup-like material, right, that you study.
Yep.
And from talking to you, we've really seen that from a fundamental understanding, you can start getting into knowledge about the world around us, solar, wind, like you were talking about, which can affect us. But then even closer to home, you have the potential to increase the efficiency of energy production than what we have today.
Mm-hmm.
So from the fundamentals, we get all the way to completely revolutionizing the way that we look at space exploration, the way that we look at energy production.
Yep.
That's amazing. And the other thing, at least I learned, was the simulation work that you do, having that validation and verification where I guess the model of science a long time ago was kind of isolated groups or isolated individuals working. You now have all this potential collaboration where you can start modeling your experimental data and look at those simulations to bring us closer to having an actual device with your plasma physics, right?
Yep, and this is also really important for the aerospace industry because they would really, really like to have models we can believe. So that's why the aerospace industry is actually leading this verification validation effort, because if we ever get to the point where the models are so trusted and like so well understood that we can get away without doing the wind tunnel experiments, it will make a huge savings for them. So that is one of the motivations for that.
Wow, that's amazing. And then Hall thrusters, energy production, tokamaks, and stellarators. All of these things are on the cutting edge of revolutionizing almost most parts of our life. Yeah. And then
don't forget about the electronics manufacturing using plasma and like all this stuff. So in industry, plasma is a big deal.
Big deal. So something that someone might not think about, plasma physics, right? Fundamentals, has led us to the cusp of just changing everything we know. And then just idly thinking, right? So if we were able to develop Hall thrusters for deep space exploration, I don't know, xenon seems a lot safer than, say, hydrogen fuel cells that can blow up because hydrogen can easily combust, or conventional fuels. Mm-hmm. Why don't we have, Hall thrusters for, like, our vehicles? way down the line. But I don't know. You probably have the answer as to why we can't do that. But
because Hall thruster would not push your car that much.
No problem.
These things these things really works mostly in vacuum, so it will be really hard to.
Well, this is why you do it, to figure that out, right?
Yeah, not really. But no, like having fusion reactors in our cars, I don't see anything bad about it, right? Nothing bad can ever happen from that.
I don't see any downsides to this whatsoever.
Yeah, me neither.
This is like the closest to a free lunch we can get.
Yep.
So, Peter, we really appreciate it, and I just wanted to ask, is there anything you want to tell our listeners as the last point, or anything you want them to walk away knowing?
For some reason, plasma is really not a topic that is on mind of many people, and it's not even mentioned in the undergrad education in the United States. But it's really important and really all around us, and it's really cool field of study. And also then you can have those really shiny plasma balls, right? You can buy on Amazon and you have those lightnings coming from it.
Yeah, I had one as a kid.
Yeah.
Yep. And the aurora borealis is also plasma, right?
Yeah. Well, it is connected. So the auroras are as a result of the particles from solar wind. So yes, plasma is all around us.
Man, plasma's all around us.
Yeah, who knew?
So
now I do.
Yep, now I do. I've learned a lot. So next time you're, sitting around, think about plasma. I know I will. Wonderful. Well, thank you for tuning in, and we'll give another big thanks to Peter.
It was a pleasure being here.
We really appreciate it.
It's really great having you.
And
Very cool
so
stuff.
I think this is a great start to season 2.
Mm-hmm.
Thank you for starting us off. So
Kicking us off for season 2.
And if you have any questions,
comments, or concerns, you can contact us. So you can contact us on Gmail under prtcast@gmail.com. You can also find our social media under prtcast on Facebook, Twitter, and Instagram.
And Peter, is there anything you want to plug before we head out?
Not really. Maybe if someone is interested more in what we do, I work at Virginia Tech with a group of Professor Srinivasan. So if you just search a name at Virginia Tech, you can find much more of what we do. We have some nice pictures there.
I can post her research page
Okay.
on our Facebook.
Sounds good.
Yeah. Or just look up really cool plasma physicist guy, VT. Bam. That's what I do.